should go to the overall IETF agenda. Yes, we are waiting for Pamit to connect. Okay, hello everyone. This is CFRG. My name is Stanislav Smishlev, and together with Alexei Melnikov and Nick Sullivan, we'll be chairing this session. And as always, we'll start with chair slides. We have the minute taker. Thanks a lot to Rich. We have a Jabber comment relay. Thanks a lot to Valerie. This session being recorded, and we have a note well. If you haven't read it yet, please do. We have quite a busy agenda, and if there is any agenda bashing, please go to the mic and say, speak up. Okay, then let's go. So the agenda and slides are available at the data tracker, and we'll start with a reminder that CFRG is a part of the IETF, not just a working group of IETF, so we have some slight differences from the way of work of working groups in IETF. And we'll tell a little more about this based on some discussions on the mailing list and offline. So first of all CFRG documents come together with some research papers, and if you look at IACR ePrint and you search for CFRG, you'll find a lot of research papers related to CFRG activities, namely PAKes, elliptic curves, HPK, AAD modes, routine mechanisms, etc. So research papers are not the direct outcome of the CFRG work, but this is what we encourage people to provide, to make during the evolution of the draft. And that's why we've got a lot of research papers related to our mechanisms. When we have a new proposal for some problem or some candidate mechanism, we are always happy when the first maybe draft version of research paper, of some security assessment, security analysis is available for any candidate mechanism. That's why we always ask people to present and talk not only about the mechanism itself, but its security properties as well. After the adoption, we encourage people to provide some additional security analysis, and the documents are updated accordingly because we need to be 100% sure that the mechanism described is the same one that has been evaluated in the research paper. When we are close to the finish with the document, we ask our crypto review panel to provide a security review. And after the review is done and after all concerns are addressed in one way or another, we have a research group last call. And of course, we always try our best to move together with academia to understand that there is some kind of academic consensus on the problem we are thinking of. And that's why we always love to start with the problem, not with some mechanism, so not to start with a good answer to the question that has never been asked. We like to start with the problem. We have two known pain points. The first of them is that some people want CFRG to move faster, to provide recommendations faster, to provide guidance faster, but we need to be absolutely responsible for every mechanisms we are going to recommend. That's why we have to wait for academia in some cases or for some additional reviews, and crypto review panel reviews are not very fast because people don't just check that the test vectors are okay or mechanisms are described correctly. They always assess security analysis, and that can require some time. And another pain point is that we occasionally get some requests for documents with primary goals to provide some implementation guidance or to block implementers, and that's also about our will to start with the problem. We've got a lot of lessons learned from two big processes that we have: elliptic curve selection, PEG selection. Now we have 9 years of work of crypto panel, and thanks a lot to all people who have been part of the crypto panel. Now we have 9 members, and thanks a lot to all of them. And now we have our starting work on combiners, which lead us to some new discussions. Nick Sullivan will tell more in his presentation, and I'll ask a question just to request for some ideas, maybe on mailing list. We understand that somehow we need to provide some new focus on what CFRG is meant to do as an IETF group somewhere, maybe on some separate web page, maybe on some wiki page, or maybe we should even think about recharter to explain this. At the same time, we can remove reference to MD5 from the chatter. And there are some ideas about these words we would like to say. They are on the slides. They're about open expert analysis. This is about guidance to inform and provide choices of cryptography that we are very sure of, and that we don't standardize protocol of algorithms. We provide guidance. There will be some more information in next slides related to ChemCombiner's design team. We have no new RFCs since November, but we've got 3 documents in RFC editors queue, one more document that has already been sent to the RFC editor. We've got 3 documents in research group last call. One of them is ages. We have some minor IPR issues with this, and Alexei is dealing with them now. We've got a very interesting discussion on the mailing list about the second document. It's AAD limits. The discussion is about security assessment, security bounds, and we are sure that we need to wait for this discussion to conclude in one way or another, because it's about the security properties of this document. And we have our DNHPKE document, which has been updated, and there are some questions about it. Maybe we'll be able to talk about it offline if someone wants. Alexei is trying his best to handle it. We've got 2 documents in CryptoPanel review, RSA guidance and VDEF. We don't see that there are any big problems, big issues with any of these. I think that we'll be able to provide them soon. And there are a lot of active CFRG drafts. All of them are quite active. A lot of them are updated, and we hope that we'll move with all of them as fast as we can. We've adopted 2 new documents related to BBS suite, and I think that during one of the presentations today we'll know more about them. Another pain point was, and still is, the status of errata. We've got a lot of errata that are not solved by now. We're trying our best to handle this situation, and thanks to Nick, now we have much less errata in this list. But anyway, all CFRG erratas are quite difficult to handle, so if we have any volunteers the room or on the mailing list, please tell us, because we really need assistance here. There is a lot of work, and we'll be thankful for any help. If you have any questions to me about these slides, please speak at the mic. Yes, Colin?
Hi, Colin Perkins. I would just like to thank you for doing the errata. I realize this is a big job. A lot of these errata are difficult to sort out. A whole bunch of these got cleared. I think that was great. So thank you very much for doing that. And I would encourage the group to try and clear the rest. I think this is actually important to do. So thank you for putting the work in.
Thank you so much. Thank you so much to Colin for his guidance all these years. And we were absolutely happy to work with you as an IETF chair. Thank you so much. So I'll pass the slides to Nick. And I'm now sharing Nick's slides. And here is the clicker. I hope it will work. So Nick Sullivan.
Thanks, Stanislav. All right, so Chem Combiners process update. Well, before we jump into Chem Combiners, I want to take a step back. There have been some messages on the list that have led to some self-reflection by the chairs, how the CFRG works, especially in comparison to an IETF working group. So what does the IETF and IRTF, how do they work together, right? You can tell in the logo. The IETF is engineers, right? It's people building things, and the IRTF is a connection to outside communities, whether it's research, whether it's policy, whoever it is that has relevant insight into IETF work. There's a give and take here. So one way that they connect together is sometimes the IETF needs some help, and the IRTF, steps in and helps them. So what could be an interesting thing to look at right here? This is a typical IETF working group standards track document. And yeah, I'd like to think of the IRTF as looking a little bit deeper and looking further, connecting communities, whereas the IETF is engineering, right? And so how does the IETF do work? Well, someone comes in with, I want to do this thing. The group adopts it, and it goes through this spin cycle. And this spin cycle includes specify, deploy, analyze. So this is a feedback loop that feeds into the document, and then it goes to consensus last call and becomes an RFC. So this is all well and good, and but it doesn't map exactly with an IRTF group. So for example, for most IRTF groups, the shape is similar, right? There's this path, there's a spin cycle, and then there's a confirmation path. But the steps are different. Rather than a proposed standard, it's often a research topic. Rather than just adopting the work, there's more scoping and conversation about adoption. And the work itself is not specify, deploy, analyze. It's do research, write a report, validate that the report is correct with respect to the research. And then this goes through the consensus last call as defined in the IRTF. Now, the CFRG is a special case, but it is relatively similar. It starts with, and this applies to basically everything that we've done in the last 9 years since the crypto panel's been around. What comes to the group is not, here's work that I want to standardize, but here's a problem we have to solve. And it goes through scoping and adoption, and then goes through the spin cycle of literature review, write things down, validate, again, through a consensus last call. And so all the work that the group has done in the last few years fits into this shape, which also fits very easily into our charter. And the key here is that it starts with a problem to solve, not a solution. Now, I can go a little bit deeper into what these steps are. So scoping and adoption, there's a number of questions that need to be asked, like how big is the problem, which IETF groups need a solution, which aspects of this problem need to be studied to avoid revisiting later. We don't want to publish 1,000 different updates on a particular topic. Does the group have the expertise needed? Are there practical requirements such as performance, size, security, things from the implementers? So that's the scoping and adoption step. Then there's a literature review. Are there security proofs? Are there reference specs? It's really good to start this process with some reference specs that you can analyze, but it's not necessary. Then there's the write it down phase, which is a collaborative writing process. And so oftentimes there are editors chosen by the chairs who are guiding this process. And for larger works, this editorial team works with the broader group to write the document in a collaborative way. But the outcome can be one or more documents as specified in the scoping. We expect specifications that come through this process to be useful, right? Potentially to be able to be referenced normatively in IETF documents. So pseudocode and test vectors, validation against implementations. This is a higher bar than you'll typically see at some IETF groups, but because of the way that it's being used. The final step here in the spin cycle is validate. So there's community review, crypto panel review. Some questions that are asked are, do the documents match the scope that was adopted, and are the security proofs reference valid? Is there a need for a scope change? Have things changed from the groups asking for an answer to this problem? Has the problem grown in some way? So now that we have this together, we can actually just map this to some of the CFRG things we've done in the past, right? So one of the more straightforward cases here is memory hard hashing. So the way this came through is there was a problem statement and a contest winning solution. This draft got adopted as with some discussion about the scoping of how much this should cover. This was Argonne 2. And then it became a research group topic and went through the spin cycle of literature review, write it down, validate, community review, all the way through consensus last call. And then we ended up with 9106. So this is the easiest case, or one of the simplest case, because the problem statement was relatively simple. It's memory hard hashing, and memory hard is defined in a certain way. So what's a more complicated process that we've gone through? Well, this is the PAIC process. And folks here are familiar. This is one of the more heavy processes that we went through. And part of that is because the problem statement itself was relatively complex. There was conflicting requirements or definitions, security properties, things like round trips that need to be considered. But the way this process followed the path was we started with a requirements document and defined a contest format, and then went through the spin cycle. We had literature review. We also had candidate draft submissions that were reviewed. These were written down. They were validated by a group of experts, and the results were discussed on the list. And after this had gone through a first round, the chairs then adopted CPACE and opaque. This was not a literal call for adoption on the mailing list. It was just part of the process defined by the requirements. So CPACE and opaque are now in the queue, have CPACE and opaque as was mentioned in the RFC editor's queue. And so we're very close on this. So bringing it all back, that was a lot of setup for this slide. And so where are we with this hybrid chem combiner process? Well, it wasn't as simple as memory hard hashing, but also not as complex as PAICs. There's only certain ways to combine chems. But there are a lot of requirements that needed to be sorted out, and we were looking for providing something that was maximally helpful to the IETF while also being sensitive to speed and velocity here. So the problem statement was adopted. There was a design team that went out and put together a scoping document. This scoping document was published to the list. We discussed it 8 months ago in Vancouver. It was adopted. We're doing the literature review. We have editors who have volunteered. to the chairs, and we're in the write it down phase, right? This is where we are. And the hope and the outcome here is that we'll have at least 2 documents coming out of this, one generic chem combiners doc and one concrete combiners. So given this and given where we are in this process, we thought it would be useful to ask some questions for the group to gauge where we are. So Alexei, do we have a Meet Echo survey that we're going to put prepped here? So there's going to be a couple questions. First of all, let's see. Okay, we're asked to list. First, who's read the design team output and scoping text? Do we have, you can raise hands here, or I see a bunch of hands in the group, and then also we'll have some in the show of hands in the slide tracker. Okay. I think are we good to close at this point? Still going. Okay, still going on this one. Results are coming in real time. So there's at least a dozen people who have read this design team output scoping text, and several people who haven't. Okay. Yeah, that's enough. Let's move on to the next one. So the next question is, who has read our current draft, which is draft IETF CFRG Hybrid Chems 03. And this should be coming up in the Meet Echo survey. Again, okay, so who's read this draft? And as a reminder, this draft is meant to be a first step in fulfilling the design requirements that were laid out by the design team and the scope of the work that is adopted here. We had discussed publishing more than one document here, splitting out the concrete versus generic. That is yet to be done on the editor's list, I'm told. So lots of people have read this, over 20 on the list. And one person has no opinion on whether they've read it or not. So I think we are good on this one. A couple more requests coming in. Okay. Now, this question is really for everyone who answered yes to both of these. Is this draft, according from your perception from reading it, on the way to addressing the goals outlined in the scoping text? Are we on the right track? And yes, if you didn't answer yes to the previous questions, feel free to answer no opinion. Okay, we can close that. It seems that we have. People who haven't read either, or haven't read one or the other. It's yes and no is people who have said yes to the first two. So we have 11 people who say yes, we're on the right track, 4 people who say the document is not on its way to addressing the goals outlined in scoping text. Third question here, fourth question, is the velocity of this draft sufficient for the needs of the IETF groups that would benefit from this work? And velocity at CFRG is driven by the overall complexity of the work, the urgency as driven by IETF and other network security in general, as in our scope. Also, efficient editorial management, community feedback, and questions and comments from the group. Things move faster when more people are involved. So let's see, is it moving fast enough? It does not seem to be, yes, very few people are saying yes, let's say. Okay, so given this outcome and the fact that it's not universal, that the fact that the draft is on its way to addressing the goals outlined in the text, and that the velocity does not seem to be sufficient, who's willing to help in this collaborative writing process? Is there anybody who wants to volunteer for editorial help. And please, we've got 2 hands in here. You can also post in the mailing list as well, or step up into the queue. Put your names in the notes for the Meet Echo as well.
My name is Richard Barnes, and I volunteer as tribute.
Thanks, Richard. We have Rich and then Mark Thompson.
Sorry, Rich Salzakamai. One option is close it. Stop the draft, because people are moving ahead without the advice. I don't know which group, I don't remember which group asked for advice and something work here. There's enough other things to do, so maybe we should just give up or stop. Declare victory and move on.
Let's pause the queue. We have quite a few in the queue. We're going to pause it for now and then open it up to broader questions after. So thanks, Rich. Martin.
Martin Thompson. I'd like a little more clarity from this. I was looking for more from you in terms of how you were going to deal with the constant back and forth and fighting about things that I concretely do not care about. This is a massive waste of this group's time, and it is sucking a whole bunch of air out of the room. And we could be doing useful work. There's like a huge amount of things on the slides that we saw earlier, and really questions about how many hashes and whatnot really does not matter. I would prefer this group not specify them than continue down this path.
Yep, there's a number of options for speeding this up other than getting additional editors on board. That could include interims or other sessions to deal with the specific questions that are coming up. John Matson.
Thank you. I previously expressed that I wanted a general algorithm. I think that is still needed for HQC, but for MLChem, I think X-Wing is perfectly fine. It's there. It's already registered in several. So I would say we don't have time to wait for this. This will probably take time, but we need some general combiner to use with other chems. MLChem is not the only chem. I don't care where the hash would be. I would recommend progressing with this, maybe removing the ANA sections.
Okay, thank you. Chris Wood.
Yeah, Chris Wood, to Rich's, I guess, request to drop this, I don't believe we should. One of the primary contributions of this work is allocating code points for HPKey to use these new chems. Well, we need those. I don't care like how those are allocated. It could be just a random independent draft that like just goes to the registry or to the INA people and says like, can we have a code point, please? We could go to the independent stream. We could do the work here. At the end of the day, we need like a stable draft that has a code point, and whatever we can do to achieve that would be good. This draft is on its way to doing so. The more people who contribute to the text, discussions will help accelerate the process towards getting those code points. But I strongly believe we should not abandon this. X-Wing is fantastic, and as John said, it's already registered. We already have code points to use that, which is fantastic. I hope people do continue to use it, but it does not cover all application needs right now. So I think that's it. Thanks.
Yes, and just a reminder to folks, this discussion is being driven on the mailing list, yes, but also on GitHub. There's a lot of conversations on GitHub, which will be summarized to the list as this speeds up. Russ.
So I completely disagree with Chris. So the HPKE work should be forked out and just get the code points. This came from LAMP's in the composite chem work and said, hey, what's the best way to combine the two chems? That work is like near done. So you're not influencing it, which was the hope.
I will say that there's other groups who have asked for this other than LAMPS, even though that was one of the first motivators for it. But thanks, Russ. Okay, we can unlock the queue if there's any general questions that are not related to who's willing to help, although these were definitely general comments. Okay, we will continue with our regularly scheduled programming.
Okay, please, BBI signature sheet update. Wesley Scalos and Greg Bernstein. Please.
Vasilis, are you there? Are you going to take this?
Yes, I'll try my best to hand over control to you. Greg or Vasilis?
Yep. Can you hear me in the room?
I've passed slides control to you. Please start.
Great, thank you. So, hello everyone, my name is Vasilis. I'm going to talk about the BBS signatures related documents. First of all, let me thank you, Greg, that made most of these slides. So, 3 documents. The main BBS signatures document, and then a blind signatures and the pseudo extension. Every one of them building essentially the previous one. So blind signatures are an extension of the main core, let's say, signature document, and then pseudonyms are building on blind signature. So on BBS signatures, a quick reminder, we have essentially a very similar model with the W3CV seal work. We have a signer, a prover, and a verifier. The signer signs an order set of messages with a single, let's say, constant size signature, and then the prover can create what we call presentations, which are essentially proofs of possession of the signature while selectively disclosing any subset of the messages they want. And everything in a zero-knowledge manner. It's what we call allocability in some places on the drafts. Some status update there. The main thing is that we have multiple interoperable implementations. Most of them are open source. And we are on the process of addressing the comments from the crypto panel review. Moving on now to the newly adopted extensions. First of all, blind. The difference here compared to the main document is that some of the messages that are going to be signed will not be known to the signer. So the prover will use this new commit operation that will produce a hiding commitment over some messages of their choosing, together with a proof of possession of those messages or of correctness of the commitment. Send that to the signer will validate it, and then use blind sign that will create a signature over messages both chosen from the signer and the ones chosen by the prover. And then the prover will use the normal proof generation and proof verification operations to create a presentation for the verifier, selectively disclosing essentially whatever they want from their committed messages and the messages that the signer creates. So main difference here are in the issuance flow. The presentation flow is almost the same as the main presentation flow from the main document. So we've done here, refined the API. We have added full set of test vectors for both cipher suites that we support. And we have at least 2 independent implementations that have verified those test vectors. Some things we want to do, refine the API more, even more, discuss what we want to generalize, how we do abstractions, and how the API should be saved. So this is a fairly new document. So editorial reviews, there's still work to be done here. A reminder of the API, but I'm going to move on from that into pseudonyms. So pseudonyms are building on top of blind signatures draft. Essentially, a pseudonym is a value that will accompany the proof created by the prover. So it will be part of the presentation that is bound signature, constant in inside a context or for a certain domain, and unlinkable across contexts or across domains. So, for example, for a specific verifier, the pseudonym value will always be the same, but across verifiers, the pseudonym value will be different and unlinkable to the previous one. So here, we extend, first of all, commit and blind sign operations that we had on the blind signature graph to be commit with NIM and blind sign with NIM. So this is essentially the same operations with the addition that one of the messages committed by the prover will be a random secret that they choose, and the signer will add some entropy to that pseudonym secret themselves, right? So they will create their own randomness and will add it to the randomness that the prover created. And then we also have to update the proof generation and verification operations from the main document to also calculate the pseudonym value and to also calculate the proof of correctness of the pseudonym value that the verifier will have to check as part of the proof verify with NIM operation. So moving on, high-level feedback. Again, this was meant to provide a way for what we call control or limited linkability when the prover revisits a certain verifier or a certain application context or domain and so on. All that while maintaining general unlinkability and addressability again across contexts and across domains. So, updates and what we want to do. First of all, we updated the API. Again, we have a full set of test vectors with at least 2 independent implementations verifying them, and at least 2 open source implementations as far as I know. What we want to do? First of all, editorial updates, better explanations of what pseudonyms are, what are the intended applications, what are the types of pseudonyms. First of all, we do also want to change the name to pseudonyms of the graph, because right now it's control linkability or verify linkability, something like that. We do plan to change that to just PPS pseudonyms. We do have to add the security and privacy sections, refine the API, refine how general some of the operations might be, and so on. And one main thing, and a question for the group as well, that we will have to consider for the privacy section is that pseudonyms compromise a privacy property that the main documents have, so the core PPS signature document and the blind signature document. And that is that those constructions have what we've described as everlasting privacy, meaning that even in the presence of a post-quantum or a quantum computer able to break discrete lock, the privacy of representations created currently will not be compromised by such a computer. This is not true for pseudonyms. If you use or the way we currently describe pseudonyms, the current construction, this can compromise that property, meaning that the privacy of presentations currently created could be compromised through the pseudonym. So a question is there a need to add a pseudonym construction that will solve this issue, right? So it may be a simple pseudonym construction that is faster, more efficient, but doesn't have the everlasting privacy property, and maybe a more complicated one, potentially more complicated one, that will not have that issue. Is there a need for such a construction? So, moving on, I think I'm going to skip those last slides. This is just an explanation of how pseudonyms works. But on the interest of not going over time, let's skip this. and this as well. It's just an API reference. Some explanatory text we plan to add were correct prepared for pseudonyms, the academic works behind them, and that's pretty much. So thank you all, and I will be more than happy to take questions.
Thank you so much. Questions? We've unlocked the queue, so any questions, comments?
I have a problem because my queue is broken, so I can't have a queue here. Can I have a question currently? I have a question that how could you implement the hash-to-curl method? As far as I know, currently there is not a standard implementation of the hash-to-curl algorithm.
I'm not sure what you mean standard implementation of the hash-to-curl. There are various libraries and very good libraries, in my opinion, that do implement hash-to-curl for the curves that we use on this talk. I'm not sure if that answers the question.
For example, on which programming language, such as Python or C or Java, do you implement your prototype?
Most of them are in C with various APIs, exposing various APIs in Java, even Python, I think, Rust.
JavaScript too.
Oh, okay.
This is I mean, there is a hash-to-curves draft that that those libraries conform to.
Yes. Okay, thank you.
Thank you. No more questions?
Okay. So here's Guiling from Huawei, Singapore. Yeah, 3 drafts about BBS is very interesting. Yeah, but my question is that I'm sorry, I have not read the draft through. Yeah, just have a quick look. My question is that, yeah, a number of things like, especially about the linkability, sometimes is quite tricky. So I would like to know your proposed draft is based on some publications, or yeah, do you have any strong link with some publications? Because otherwise, yeah, sometimes, yeah, the security could be very tricky. Is my question. Thank you.
Yes, thank you. Yeah, we are. So there is a long line of academic work behind BBS. We are heavily based on the latest, at least as far as I know, latest work from Crypto 2022 or 23. I can't really remember. The work is called Revisiting BBS Signatures. It has extensive security analysis on multiple models. This is mainly what we use, which in itself is heavily based on previous works, right? It's not a complete revision, let's say, of what was previously there. It's just shrinking the signature a little bit, or shrinking the proofs a little bit, and stuff like that. So that's what we use.
Yeah. Okay. Thank you. I will try to read your drafts later. Thanks.
Thank you.
Thank you.
We'll have to finish with this, and please, Chris Wood, anonymous credentials. Please take the clicker.
It's work.
Yes, it's working.
All right. Hello, everyone. I'm going to talk about a new proposal we have called Anonymous Rate Limited Credentials. Before I get into the sort of high-level overview, going to paint a story of how this came to be, starting with Privacy Pass. For those of you that are not familiar, this Privacy Pass is a protocol for sort of anonymously authorizing or authenticating clients for various things, like connecting to proxies and whatnot. The way it works is client sends like a request to an origin, a server, and the server can say, hey, please give me a token to authenticate yourself anonymously. Client will then sort of run this protocol on the side between the two parties, an attester and an issuer, to get a token, and then it will reattempt its request for providing the token to authenticate itself. Cryptographically, this is all very simple. The token challenge is basically just a nonce that the server provides. The issuance protocol to produce a token is just blind RSA or the VOPRF, pick whichever one you like. And then actually verifying the signature is a matter of, or verifying the token is a matter of verifying the RSA signature or computing the VOPRF output and checking it against expectation. Nothing fancy. However, successful, I guess, the initial version of Privacy Pass is, it does have a number of limitations. In particular, there's no ability to rate limit individual clients. And that's because sort of by design, when a server asks a client for a particular token, it doesn't learn anything about that client. It just knows that it presented a valid token. It doesn't know that this token happened to come from a client it's interacted with in the past. Or anything like that. And because of this property, it makes it very difficult to enforce sort of per client rate limiting, which is important in some applications of Privacy Pass. Another limitation is that every single token must be bound to one particular nonce that's provided by the server. So every time the server asks for a token, the client must have already gotten and fetched the token, or must do so fetch one in real time. So this is like linear cost associated with it, which is not fantastic. So I would say, to summarize Privacy Pass right now, it's built on very simple primitives and widely deployed primitives that we understand and we know how to use. But from a deployment perspective, this lack of per client rate limiting and this sort of expensive token to issuance cost can be prohibitive depending on what issuance protocol you're using. So from those limitations, the Privacy Pass group attempted to introduce a new protocol contorting itself to use as many of the existing primitives as we could to sort of implement rate limiting in a way that made sense. It introduced a complicated protocol with a complicated deployment story that at the end of the day, if you align things just right and correctly, it will work. But it has a number of sort of prohibitive problems that might make you not want to use this in practice. Beyond the complexity, there's this, you need non-collusion between all of the parties in the system for the privacy goals to sort of come to fruition. And even with that, there is some sort of controlled amount of leakage that takes place in the protocol, which is not ideal. And something we can get away with if we use other cryptographic techniques. And finally, it doesn't even address the cost of one issuance request, or the one-to-one cost between issuance and tokens, which was another thing we wanted to deal with. So taking a step back, we thought maybe it'd be useful to look again at the design space for different ways to solve this problem, and anonymous credentials were sort of, I guess, obvious in hindsight. And I guess for those that are, I guess, unfamiliar, anonymous credential is a way to allow, as the slide says, sort of selective disclosure of attributes that are bound to a particular credential. So these attributes might be, for example, private metadata bits that you might want to use for your application. It might be like a pseudonym, as the previous presentation was just talking about. It might be, various properties used for rate limiting or issuer hiding. It's kind of super flexible. You can do a lot of things with them. In practice, there are a lot of ways to instantiate anonymous credentials. So we have CMC, we have BBS, and so on. The publicly verifiable version of these credentials, which is in the BBS flavor of drafts right now, uses pairing-friendly curves. But for applications or deployments where that's prohibitive, you might want to use a key verification version that relies on standard curves, like Unis curves, curve 2519, and whatnot. But both are possible, similar to how we have privately verifiable VOPRFs and publicly verifiable blind RSA. So ARC, or anonymous rate limited credentials, is a very, very specific instance, an opinionated instance of an anonymous credential that was constructed with the sole purpose of punting out this experimental rate limited privacy pass protocol that we designed that was built on RSA and coming up with something that's a bit more modern. Came out in 2014, so I guess modern is questionable, but a lot more suitable for purpose. It is, unlike the BBS variant right now, it is a key verification anonymous credential, which means you require, it's not publicly verifiable, you need the private key in order to verify it. And it has exactly one extension or attribute, and that is, that pertains to rate limiting, which means that, functionally speaking, the client is limited in terms of how many tokens it can produce from a single credential before it needs to go fetch some more. And it's also generalizable to the key verification version of BBS, which is technical detail that we can talk about offline. But there's a lot of flexibility with regards to how this thing is constructed. So the syntax is actually quite simple. If you think of like the issuance protocol for a credential, the client inputs what we call a request context, the server inputs a private key, and out pops a credential for the client to use. The server gets nothing out of this exchange, pretty straightforward, I would say. And then later in presentation, if a client has a credential and wants to present it, it inputs its credential, presentation context, a different thing, and then a presentation limit, which is like the rate limit. Server inputs its private key, its request context, presentation context, and presentation limit as well. They run the presentation protocol, and the server learns whether or not sort of the presentation that the client did was valid, so it was correct with respect to the credential. And the client gets an updated credential, which it can then later on use for producing another presentation up to the rate limit. So it can go through this process many, many times, depending on what the rate limit is. And once it hits that rate limit, the client can't spend or use the credential again without violating its own privacy. You effectively lead to a double spend sort of scenario. Okay, there's a lot of technical details in there, but I don't think those are really important. I think the sort of big picture of like what CFRG is doing in the space is more important right now. So on the slide, I apologize for my sort of poor art skills, but what I tried to describe is basically what CFRG is doing today and what we're proposing and how they sort of blend together. So on the right-hand side, you'll see sort of the BBS layer specification. So we have like the verifiable linkability thing that was just presented, as well as like the blind BBS signature specification. That is work that CFRG has already adopted for a very specific use case of pseudonyms on the web. On the left, we've specified ARC, which is like the privately verifiable version or complement to the BBS flavor of things, built with the intention of implementing rate limiting and privacy pass. Probably should have slapped these slides around, but that's okay. Pin that image in your mind for just a moment if you can. I apologize. Just to quickly summarize what ARC is all about. It's the privately verifiable version that complements the ongoing work in CFRG that's specifying BBS. It has a bunch of internal things that can be swapped out or changed or whatever that fundamentally don't really matter at the end of the day, provided there's a proof of security that the swapping out of things is correct and can be done so safely. And it satisfies a direct need for a privacy pass, which is why we're here in the first place. Okay, so my proposal for the group is to kind of rein in a bit, I guess, the work that the CFRG is doing. So right now we seem to have this, this set of drafts that are focusing on BBS-specific constructions for this, per verifiable linkability, the pseudonym and extension. It's basically building an anonymous credential of a very particular type. And anonymous credentials are, I think, a topic that warrants more thoughtful exploration by a research group such as this. So I think it would be useful for this group to sort of invest in sort of the mental model and the framework for how you use anonymous credentials in practice. Very similar to how we talked about building a sort of, or writing a sort of generic chem combiner draft. And this would be sort of conceptually like an architecture framework draft for, if you're an application thinking about anonymous credentials, here's the things you have to consider. And then go further and specify like concrete instances of these anonymous credentials. So we already have the BBS work well on its way of doing this. ARC would complement that in the privately verifiable setting. And then there's various pieces internally that are shared amongst both of these drafts that can be pulled out and factored out, similar to how we factored out things like hash to curve. So for example, both drafts now specify basically a way to build a zero knowledge proof that could be easily split out. And in fact, Michele is going to talk about this after I'm done. And so I envision something like this that the CFRG works on. You have sort of a framework for anonymous credentials. Within the work that is scoped by that particular framework, you have specific instances of the credentials, one of them being ARC, one of them being based on BBS. And the distinction is that one is publicly verifiable and the other is not. And then there are sort of core fundamental pieces that are factored out and worked on, like the zero knowledge proof compiler or whatever else is necessary for this work to be done. And yeah, that's it. Happy to take any questions. I'm curious to hear what folks think about the feedback on the proposal, especially given the chem combiner stuff that we were talking about earlier.
All right, Julian from the queue.
Was he left over?
Whelan. Okay, let's move on to Deirdre.
Hi, Deirdre from Sandbox AQ. I think this is great work. There's one concrete cipher suite in there based on P384. Cool. Maybe one based on anonymous curve.
Yep.
Like it needs a primordial group. Ristretto.
Yep.
We love
Sure.
Ristretto. There are anonymous credential constructions that are theoretically PQ. Thinking about writing down new crypto that's quantum resistant. Maybe we think about it.
I think, yeah, so I think it's prudent for the group to consider what the post-quantum properties of these things are, post-quantum privacy properties in particular. I don't know what that looks like concretely, but I would expect that to be a consideration for any new work that we embark upon.
Yeah. Cool. And the 3 document proposal seems like a lot of moving parts. I would be in favor of adopting this work kind of as the skeleton it has, kind of like a more generic kind of privacy pass design. Like, okay, these things are related, these pieces of work are related, but I would be fine with just having like, we're doing ARC. This is ARC and we're moving it together as like a unit. And I'm fine with that, so.
I think we will be as well, but like in discussions with the various people working on the other drafts, there emerged sort of this observation that we're all rewriting the same exact stuff and doing it slightly differently, which does like pose various risks. For example, you might take like a compiler from one specification and try to use in another, and it's unclear if that's safe. So we do what's best for like the actual implementer and the application using these at the end of the day, and if that means a slightly more complicated structure to build those safe abstractions up, that would be my preference. But I think technically speaking, we could just ship ARC as is, and it should work. It's just, is it the best outcome for other drafts and other work? Unclear.
Please, Valerie. A related question from the chat from Michelle Oru. Thank you for your hard work. I checked the spec and I'm concerned about the core scheme and anonymity. The core scheme is not CMZ. Where is the formal analysis of a different scheme? Concerning anonymity, it doesn't seem to satisfy the canonical definition of anonymity. What security definition do you satisfy? Would you be amenable to learning to a proven construction?
I'm not sure I caught all of that, but we are absolutely open to like improving the specification, whatever. Yeah, I'll take a look. And Michele and I can talk offline. But yes, to be abundantly clear, none of the stuff, we are fixed to none of it. All of it can be swapped around, like all of the cryptography under the hood and the design of the protocol itself could be changed. The nice thing about these anonymous credentials that are based on CMZ and BBS is that they're very generic, sort of plug and play. So yeah, I think we can make that work.
Okay.
Not having understood the question entirely, but sure, why not?
Thank you, Raphael.
Yeah, I think this is very interesting because it seems like the motivation behind it is exactly the same one I had for the badge tokens, privacy pass. And it looks like this is solving it better than the badge tokens, but I'm having a hard time wrapping my head around what the net benefits are really. It looks like it's less expensive during issuance, but it's the same during redemption. And in terms of security and privacy guarantees, it's pretty much the same, right?
I think it would be slightly more expensive in both cases, but the main benefit is not having to run the issuance every single time you want to produce a fresh token. So for your case in Privacy Pass, if you want to challenge the same client over and over for a token, as long as the client has a credential, it doesn't even need to talk to the issuer. It just like looks at its credential and out pops a token.
Yeah, sure. But I mean, that was the whole idea behind the badge tokens, essentially, that you talk to the issuer once and you get a whole bunch of tokens.
Yeah, but like depending on how you look at it, like you're effectively asking for, you're running the issuance protocol n times to get n tokens. In this case, you're running the issuance protocol once to produce n tokens. Does that distinction make sense?
No, not sure I agree. Because with batch tokens, you only run it once and you request n tokens.
But you're one round trip, but you're like.
But it's still linear, of course, in the number of tokens, obviously.
Sorry?
It's linear in the number of tokens you request. Computationally.
Yes.
And in terms of bandwidth, yeah.
Bandwidth is not really the primary, I guess, saver.
Sure. Yeah. But it would be interesting to see what the break-even point is.
Yeah, absolutely. That would be that's a very good thing, a very good point. We should actually sort of like do that comparison to see like what's the inflection point.
Right.
Yeah.
Thanks.
We're running out of time, so the last question, Vasilis, or maybe comment. Vasilis?
Yeah. Yeah. Just first of all, express support on the proposal of factoring out the common stuff. Maybe just a comment here. We had this discussion offline as well, so it's more of a question on the group because as Chris mentioned, you can have this arc construction based on CMG or privately verifiable BBS. Should do this work of having different associations based on different cryptographic protocols, or is CMG just fine?
I'm not sure I caught that. Could you try to repeat the last bit?
Yeah, so essentially in CMG, you could have a cipher sheet based, in ARC, you will have maybe a cipher sheet based on CMG and another one based on BPS. Is this a feeder? Do people want to do this work of having the privately verifiable BPS version so it can be used on ARC? So maybe we can factor out even more stuff, in a sense, because both will be based on BPS.
Still not sure I caught it. I'm sorry, but I think Boyd should take it offline.
Unfortunately, yes, I can offline because we are 15 minutes late. Okay, thank you so much, Chris. And Michel Leroux.
Hello. 1, 2, 1, 2. Can you hear me properly?
Yes, we do. And I've passed slides control to you. Please start.
One second. Hello, everyone. This is about Sigma protocols and Fiat Shamir. It is joint work with Alessandro Chiesa from APFL and Cathy Yoon from Apple. The goal here is standardizing zero-knowledge proofs. Zero-knowledge proofs are a protocol that where the prover convinces the verifier of the existence of some secrets to satisfy a predicate that here I'm calling statement. What needs to be specified more precisely are two functions, a prove and a verify function. The proving function takes as input a secret and the public information, and the verifier decides if the proof is convincing on the basis of the public information and the messages exchanged so far. For the verifier, messages are always random and public coin, as we say. Now, in practice, we never or almost never generate those verifier messages interactively. We generate them non-interactively by applying the so-called Fia-Shamir transformation, which replaces the verifier messages with the output of a random oracle. And the objective of this first specification is to describe how to transform interactive protocols into non-interactive proofs, specifying carefully how the random oracle is instantiated, what goes inside it, and how the outputs are remapped in the correct domains. Our approach here is to rely on well-established techniques in the hash literature with duplex sponges and formalize as much as we can this transformation down to the permutation function. We do have a pen and paper proof with Alessandro under submission, and as we move forward, we would ideally also like a machine checkable proof of this. Now, once we have Fia-Shamir specified, what is the easiest, immediately useful proof that we can use? These are Sigma protocols. And the first goal for me here, at least, is specifying malware proofs, which allow to prove knowledge of a secret pre-image X under a public function phi. And they are so simple that the entire description of them fits a single slide. And they are not only not just simple, they are also immediately useful. By this, I mean that here I am displaying here I'm displaying specification that already use them. And I've been collected them into RFC, drafts, other standardization bodies, and what I call public good deployments, meaning projects that have deployed them, but don't necessarily have the loud voice here to make them happen also standards. And just to make some examples here, RFC 8235 is about proving knowledge of a secret key. And here the function is just exponentiation by G. In VOPRFs, security, it is necessary for security to prove that pre-image of true exponentiation is the same. So again, similar for the proof. And even in BBS signatures, we keep on seeing the same thing where we need to prove knowledge of a message and a signature that satisfy the verification equation. And what is happening right now is that we're always recompiling the same zero knowledge proof over and over. And as we keep on developing this specification, there is a question whether an actual layer should be built. Even those specifications that do not rely on Sigma protocols, such as the recent draft from Google or the W3C decentralized identity sort of initiative, they might require more powerful proofs, but they will still have to rely on a Fia-Shamir transformation. And so in this sense, I think the layering is correct in this way. And so my fear is that if we do not act and provide a nice zero knowledge layer, these sort of proofs, we will be exposing ourselves to redundancy in terms of implementation, in terms of effort by independent reviews, and in terms of specification. And at worst, we will expose ourselves to reuse attacks where proofs can be copy-pasted between different contexts. I do believe that there are some, if I think about the purpose of a standard, the goals for me are reaching interoperability across implementations, enhance or raise the bar for security by isolating components and relying on well-established foundations, and enhance the quality of the role implementation, maintaining those layers that have been specified for more than 30 years of research. And I do think there are also some very good opportunities here. I think this can help paving the way for generic snarks, which will have to come at some point. And these are small steps that are immediately useful. And finally, I do think that even the small steps that we're doing can feed the post-quantum agenda, meaning that some Sigma protocols are post-quantum sound, and most of them, even the ones that rely on discrete logarithm assumptions, have some post-quantum privacy guarantees. And as such, I do believe they will be also useful in the long term. This is all. I'm leaving here the link of the website where I'm putting, the draft specifications as well as the reference implementation that we're going to build, a previous specification done in PDF, and some propaganda material. Thank you so much, and have a good IETF.
Thank you. Oh, that's great. There's no questions because we're behind the schedule. Thank you so much. Let's continue. So Frodocam. Patrick?
Can you hear me now?
Yes, we do, and I've passed slide control.
Okay,
Please
let's
start.
see. All right. Okay, so hi everyone. I'm Patrick Longa, and today I'll be talking about Frodocam again at IETF 121. I gave a talk about Frodocam, giving some security features about the post-quantum scheme, the performance, talk about the performance profile, and also mention the ISO effort to standardize it. So today I'll be talking about an update about this work, and also I want to announce that we finished a first IED for a Frodocam. And this is joint work with Joe Pavos from NXP, Stefan Ellen from BSI, and Douglas Stebila from the University of Waterloo. First, let me give a brief recap about Frodocam. Frodocam is a quantum-safe in CCA2 secure key encapsulation mechanism based on the hardness of the plain LWE problem. So it uses generic algebraically unstructured lattices with the objective of minimizing potential cryptanalytic attacks. There is no algebraic ring structure like the case of MLChem. And together with other design features, one of the purposes is also facilitate simple and compact implementations. And this, we believe, also facilitate security against side channel attacks. Frodocam was a round 3 alternate in the NIST PQC standardization process. And here I put a quote from the NIST round 3 status report for the justification of dropping Frodocam, which was basically motivated by performance. And the quote says, in terms of security, Frodo's conservative design choices are laudable. All right, so as I mentioned, Frodocam is undergoing a standardization effort at ISO. This effort started on April 2023 and was started by the German BSI and immediately received wide support from many national bodies, like, for example, ANSI from France and NCSA from Sweden, and many others. So this really motivated to undergo to proceed with the standardization. The plan for the standardization effort is to have an amendment of specifically Amendment 2 of ISO IEC 18033-2. And this amendment will introduce the standardization of MLChem, Classic McLeese, and Frodocam. Currently, this amendment has been approved for draft international standard, or this, as of December 2024. And there is an ongoing this ballot, which is expected to be done by May 2025. So in summary, the process is going very well. The standardization effort is proceeding very successfully to this point. So as I mentioned, there was a strong, wide support from many national bodies, specifically, and more importantly, from several European countries. And here I am highlighting several of the statements made by several of these countries. For example, from the BSI, this is a well-known statement and statement support from the BSI, which recommends Frodocam and Classic McLeese together for as conservative options. The same similar stuff from ANSI from France. Here's another statement of support by the Netherlands, and let me read it very quickly here. There may be scenarios in which a stronger level of conservatism is desired. For these scenarios, Frodocam and Classic McLeese provide key encapsulation functionality. However, Frodocam and Classic McLeese have not yet been standardized. Until this is the case, we consider these primitives merely acceptable, although we strongly support ongoing initiative aiming to standardize them. And this appears in the PQC Migration Handbook from 2024. So it's a strong statement about the need for standardizing these conservative options. finally, I want to mention this other well, recent news, SOGIS from the EU. This is a European Mutual Recognition Agreement for Common Criteria Certifications of IT Security Products. Involves about 17 member states, and they are about to release this document, SOGIS ACMV 1.4, which will include PhotoChem alongside MLChem as options for post-quantum chem algorithms.
Patrick, you're out of time, so.
Sorry?
You're out of time, so please, could you please be a little faster?
Okay, so I'll jump to the final part. So we are about to release the draft. You can access the draft source that is in the link below. And here is to finish the call for action that we wanna state today. So the traditionally labeled conservative algorithms are not being standardized by NIST at the moment. And I hope I convince you that there is a strong support for their standardization. And so we think this could be an important action to take at the IETF and the CFRG. So the question could be if others are interested in the CFRG working on this subject, and we will continue the discussion on the mailing list. And with that, thank you very much.
Thank you, Scott.
Scott Fleur, Cisco Systems. Is there any intention to create a draft, a definition of Frodo which is not paywalled?
Yeah, no, this is basically what I mentioned a minute ago. So we have an ID that is going to be released in 1 or 2 days. We didn't release it yet because we didn't do it on time for this meeting, but it's going to be there today or tomorrow or in a couple of days. And you can access the GitHub repository where we have the current version. So it's publicly available.
Thank you, Gordon.
Yeah.
Gordon?
Thank you. So I just have a question about one slide. You mentioned the progress of the Fredo KM in ISO. Yeah, you mentioned some DIS on the May of 2025. Can you explain to us what that means? Yeah, can we say, okay, by that time it's fully released by ISO as a standard or something?
For about the status. Okay, so you're asking about the status of the year, right?
Yes.
Oh yes. So basically here on this step, the national bodies will be giving their votes if the standardization proceeds, and the results are going to be available on May 2025. And from that, they could actually say proceed to the publication of the standard, or they could go to another stage that is called FDs, if they have some technical things that want to be corrected before the standardization. So we are basically in the final stages of the publication of the standard. If everything goes well, it might be even ready by the end of this year.
Okay.
Thank you, Tom.
Yeah, thank you.
Tom Biggers, VQ Shield. I strongly recognize that ISO and paywalls are very, very annoying. But reflecting again on the first talk we had today in this meeting, what is the research question here? Are we just going to rubber stamp whatever is specified in ISO? Because clearly there's no desire to be incompatible with what is written there. So it's maybe more of a question to the chairs. Does this even fit here then?
Yeah, I just wanted to mention that just to highlight again the question or the proposal at the end of the presentation was basically, okay, NIST is not going to standardize these labeled conservative post-quantum algorithms, and there is such a need, right? So there are many entities out there that are requiring or requesting the standardization of these algorithms. So it would be interesting to study them and analyze if it's suitable to standardize them at the IETF.
But the CFRG doesn't make standards.
That's correct. So what this presentation had at the end was an opening up the discussion to talk about this on the list. And I think that's the next step. The shape of a problem that the CFRG could tackle in this arena is something like IETF groups want an alternative to ML Chem. What are the alternatives? What are the trade-offs between them? Something along those lines.
Yeah, and I'll be happy to continue the discussion on the mailing list, as Nick is saying.
Thank you so much.
Yeah, thank you.
Please take the clicker.
All right, more hybrid chem stuff. Okay, I authored the first 3-4 drafts of the hybrid post-quantum traditional chem combiners research topic. The first rough draft was delivered, not delivered, it showed up on the internet in November 2024, just after the last meeting. The first draft that was uploaded was in January. It was a very rough draft. That's why the commit message is just a skull emoji. And the one added test factors and code, thanks to Chris Wood, thank you very much. And then we added generic keygen, labels, domain separation in version 2. And now the current version is 0.3, and we talked a little bit about that earlier. So what do we have? The group said they wanted 2 documents, one with the generic hybrid constructions or generic ways to do construction, and one that had concrete instances. While drafting this, it was easier for me to just edit the 2 things together because they were all kind of moving around together. So currently we have 1 document, but if the group wants to split it up into just the generic stuff and like a separate instance of the first concrete instances using the generic recipes, totally fine, whatever. For now, it's just easier as an editor to just keep it all together. It includes descriptions of the cryptographic dependencies such as a KDF, an XOF, the different traditional components and post-quantum components. It includes 2 generic constructions of how to create a hybrid, a secure hybrid chem from traditional and post-quantum components, and includes a common generic key generation and derivation design that you can use for either of those generic hybrid chem constructions. It includes 3 concrete instantiations of those 2 designs, 2 of which are FIPS friendly or NIST friendly, and one of them is not FIPS or NIST. Well, now you can make an argument. It uses component algorithms that are not just all NIST stuff. It uses stuff that's kind of friendly in the IETF. It has lots of security property sections, one that's generic for the whole document, and specific ones for each concrete construction that we list. Guidance on how you sample elliptic curve scalars and things like that. A whole section on what is out of scope of this construction, or of this whole document, and a bunch of test vectors. So our generic constructions are the kitchen sink construction. I picked the name. It just seemed, you put everything in it, including the kitchen sink. So this is the conservative, simplest, secure construction. You put in your post-quantum shared secret, your traditional shared secret, your post-quantum ciphertext, your traditional ciphertext, your post-quantum public key, your traditional public key, and a label/domain separator. You put everything in, you can cut them all together, and you shove it through your KDF that is part of your concrete instantiation cipher suite. There it is. As in the name, you put the whole transcript of this cryptographic protocol, not the whole high-level internet protocol or something like TLS or anything like that, but this cryptographic scheme, it puts the whole transcript into the chem KDF. This relies on the minimum security properties of its component algorithms. You need a secure KDF, and for keygen, you need a secure XOF. You need an NCCA post-quantum chem, and you need an elliptic curve that has can be modeled as a quote nominal group Spoiler, basically every elliptic curve that anyone cares about can be modeled as a nominal group. Actually, you don't need that for this construction. It's simple, it has minimum requirements of its components, and it just happened to match the construction that showed up in the draft version of NIST SP 800-227. We had written this down months before this showed up, and it was just a happy accident that they are the same because they have similar, nice properties. They're simple, it gives you a lot of security, it's a little bit conservative, it's shoving all the bytes directly into your KDF, but you don't have to think much more about the security properties of your components beyond what I basically said. It does not exactly match because it's just the order of where you put the public material, like the public keys and the ciphertext, that can be moved around and everything could be the same. The other generic construction is the QSF construction, which is, the name is borrowed from the X-Wing paper, what was it? Quantum Strike Fighter, I think is the name. And this takes in your post-quantum shared secret, traditional shared secret, post-quantum. This is matching all of them. You put in all the stuff and then the internal guts, the implementation of the generic combiner takes what it needs and leaves what it doesn't. You concat your post-quantum shared secret, your traditional shared secret, your traditional ciphertext, your traditional public key, and a label, and that's it. And then you shove that through your KDF. This is relying on specific security properties of your post-quantum CAM beyond in CCA. In the X-Wing paper, this was named a ciphertext second preimage resistance, also known as chosen ciphertext resistant, and is shown to be equivalent to the binding property leak bind K, P key, PK CT, which implies leak bind K CT. This allows you to, if you pick your post-quantum component algorithm to match these security requirements, to put less material through your KDF. So if you're going to have an instantiation of, say, SHA-3, this can save you, if you're using MLCAM, over 2 kilobytes of input to your hash. So this is nice for more efficiency. There are plenty of other CAMs that you can use this for, and I think MLCAM, which we just discussed, is one of them. You have to cross-check me on that, but I'm pretty sure you can use this construction with it. But it has more requirements on your components than just a secure in CCA post-quantum CAM underneath. And for both of these, we have written down a generic key generation derivation scheme. This is very similar to the design that we wrote up in X-Wing, which is you have a seed, you stretch it with your expandable output function, and you use the output from that function to generate the actual component algorithms keygen. So this is an example of like you sample use the stretching to get those bytes out, you sample a scalar from it, you hand those seed bytes to your post-quantum chem keygen and spit it all out. And then if you have a seed, just read how you rederive it. We almost didn't have this written down. We didn't have it written down as a generic. We had the concrete keygen for all the concrete instances that we had written down, but we didn't have a generic one because we knew that one size didn't always fit all. Until Dustin Moody from NIST said in public that the updated version of SP 800-133 will allow this to be done for the applications that care about being FIPS compatible. So we were able to have one that was workable for all the instances of the generic constructions that we had, and gives us these lovely security properties. Operational security properties, you just have like a 32-byte or n byte seed and that generates everything, but also it gives you stronger binding properties for the whole CAM. It's a nice way to do hybrid key generation. So we're happy that we think that we could do one generic design for all these generic constructions. So these are our concrete instances that we have written down in this document. These are not the end-all be-all of concrete hybrid CAMs. These are the ones that we suited to instantiate these two hybrid generic constructions we wrote down just now, and to fulfill a bunch of asks from the IETF. This is not the end all be all. Please introduce new documents to the CFRG to write down your own concrete instances of the generic constructions we have in this document. I already have ideas about writing down ones for HQC hybrids in the future because NIST is going to standardize a version of HQC in a couple of years. So we have QSF CAM, MLCAM 768, P256, XOF SHIG 256, KDF SHA-3 256. Is that right? This is basically X-Wing, but with P256 instead of X25519. That's it. X-Wing is in another document, so we didn't redefine it here. The next one is kitchen sink, MLCAM 768, X25519, SHIG 256, HKDF SHA-256. So this is kitchen sink with MLCAM 768 and X25519, using the same XOF for keygen, and using HKDF as our KDF instead of SHA-3. We had people that wanted not NIST components or NIST curves. We had people who wanted not SHA-3 because they couldn't use SHA-3, and we wanted people that wanted. We had people that wanted more IETF friendly algorithms and not just everything be kind of NIST-ish or whatever. So this is trying to meet those needs. And then we have QSF, MLCAM 1024, and P384, SHIG 56, and SHA-3. This is kind of the top one, but the highest security level, because we had people who were like, I need MLCAM 1024 hybrid. And this is the recipe that basically matches that. That's what we got. And this is explaining what I just said, basically.
Yeah, you're a bit over time, sorry. Yeah, if we can speed up. Thanks.
So a bunch of stuff was out of scope. We only picked recipes that would allow you two things: a post-quantum chem component and a traditional, cryptography component. We didn't want to do n-wise parameterizable recipes. It just gets out of hand. We didn't want parameterizable output length for the shared secret. They're per instance, like finite, based on the KDF that you choose for the hybrid chem. There's a label that allows you, that you are required to put in like the recipe, the name of this hybrid chem. If you want to put protocol specific information in there, you can, but that's you defining a protocol specific hybrid chem that is non-interoperable with other instances of hybrid chem. So if you want to do that, you can, but just letting you know. And then, yeah, if you want other component primitives, go right ahead, but like there'll be a separate document. As I said, I already have ideas of exactly what I want to do there. Next, we haven't allocated IANA registrations for any of these concrete chems yet for HPK chems. We just haven't gotten around to it. There's some nits about serialization and things like that that we're going to fix. There's some to-dos to fill out in the document, especially like more information about binding properties, especially for the QSF generic construction, and any feedback from the working group. Questions?
Going once, going twice. Okay.
Lock the queue.
Okay, I just have one question. So you have two generic construction. One is the kitchen sink, one, right? Another one is the QSF. Yeah.
Sorry, can you repeat?
Yeah, I mean your two constructions. My question is that I would like to know, have you done any analysis to show the performance difference? Because in my understanding, two constructions, the input are not a big difference, especially for the setting of KEM, so the input is not a big difference. In that case, maybe the performance of both construction not big. In that case, do we still need two constructions or just combine them as one? Either experimental or theoretical analysis. Efficiency difference.
Are you discussing? I mean, it depends, because if you instantiate QSF with a very slow computational post-quantum chem that has very few, very small number of public bytes, it might be comparable to a very fast post-quantum chem, sorry, not QSF, kitchen sink, that has a lot more public bytes. Like, it really depends on your concrete instantiation for these performance comparisons to really matter.
Okay. So is it possible to give some numbers? Yeah, like if I do this one particular, this KM.
They all
this
use ML
function,
Chem for the
then-
concrete ones, so those comparisons are a bit moot. So, sorry? What, ML Chem? All the concrete instantiations use ML Chem. One of them uses 1024 and the rest of them use 768. Comparing the concrete instantiations that we have written down to each other when they are all using the same, biggest, beefiest component is a little bit like, do you get any actual useful information out of that? So,
okay.
But
yeah, maybe I talk.
we can discuss it on the list. So.
Martin, you have minus 10 seconds to ask your question. We're 15 minutes late.
So I came to this session to hopefully help work through some of the problems here, and we got a presentation and we didn't get any discussion time. So I'd just like to register that objection.
Okay.
So concretely, there are other proposals out there that some people seem very, very attached to. And we have a bunch of proposals here that you seem to have decided that those are the ones. And I'm not seeing any consensus or agreement about what the actual set of combinations are. And I think it's probably irrelevant because without a protocol, you don't need code points or anything. You don't have interoperability because it's just like a bunch of words in a document somewhere, which is useful, but I'm not sure that we need anything concrete at all.
I respectfully disagree because the fact that no one is complaining after putting up this list, after several meetings of people being like, but I need this and I can't use that and XYZ is that indicates something like consensus to me.
And go ahead and do it. You don't need me to tell you what to do.
I need a code point. I need a code point to reference something.
Yeah, thank you.
Thank you. And we have to go to the next presentation. ECDH PSI. Ivan, please.
Okay. Thank you. I'm Yuchen Wang from Art Group. Today, I want on behalf of my colleagues Wenting Chang, Yufei Lu, Chen Hong, and Jinpeng to introduce our protocol of ECDH PSI. Here, first I want to introduce the status of our proposal. ECDH PSI is a simple PSI scheme that we proposed since IETF conference 121, where PSI is a primitive stands for private set intersection, where in PSI two parties with data size A, SA, and SB, they can calculate their intersection without giving out the records that are not in the intersection. There are many real-world usages of PSI, such as checking password leakage, finding common customers, and monitoring the criminal behaviors. As far as we know, there have been many deployments of PSI in China between enterprise and enterprise, and there are also many open source implementations currently. Now, this document is under the privacy preserving measurement group, and it is highly relies on CFRG's RFCs. So we think that here is a chance to present our proposal. This is a many application layer protocol and is under discussion with many PPM members. We have received very detailed and valuable comments and suggestions from the CFRG panel, Thomas Proning and Christopher Patton. Thank you, Thomas. Thank you, Chris. And we have considered all suggestions and comments from CFRG and PPM and released a new version in the following link. Here is a brief introduction to the ECD-HPSI protocol. It's a very classical protocol seen from the private matching protocol proposed by Meadows since 1986. Like figure 1 is basically a Diffie-Hellman style PSI with elliptical parameters, where records are converted to points on curve with the hash-to-curve algorithms defined by CFRG CFC, and then they are masked by the secret keys of both parties with scalar multiplications. As shown by figure 1, it is a well-recorded example for the private matching process. If RA and RB are the same record, they will be finally masked to the same point after the joint masking process. And if they are different, they will be masked to different points, but a participant cannot recover the record RA or RB since it does not know the corresponding private key of SKA or SKB, which makes the matching private. Here is a brief introduction to the security model of the protocol. Commonly, the protocol ECD-HPSI is considered secure in the semi-honest model, but as far as we know, the malicious setting is seldom considered. We believe that malicious attackers still cannot recover the original record, that is RA and RB, but it can indeed obtain some extra information, such as the cardinality of the intersection. So our draft considers the following potential attack scenario. The first one is that the mask key, although it is refreshed in different sessions, but in the same session, it can be used by an attacker as an ECDH oracle, as suggested by Chris in the semi-honest model. And we also consider side channel attack also in the semi-honest model. And also the man-in-the-middle attack, where an attacker can obtain the cardinality of the intersection in the malicious model. Finally, a replay attack described by Cui and Yu, where Yu, for Yu, which is a cryptographer, someone we know, where a malicious attacker can obtain the cardinality of the intersection between SA and SA prime, which I will explain later. Here is a brief description of the man-in-the-middle attack, where a man-in-the-middle AM can act as a proxy who only transfers data between only the participants A and B. As shown by figure 2, after the attack, AM will finally learn the cardinality of the intersection. In the attack, AM only participates the protocol with its real identity. That means such attack cannot be prevented by using TLS with mutual authentication. Here is a brief introduction to the replay attack. It's a cross-session attack, where the attacker M runs 2 sessions with the victim A concurrently, but instead of sending its masked data honestly, the attacker masks the data masked by A in the other session, as shown by the red arrows, and sends the wrongly masked data to the current session. That means in session 1, the attacker can finally obtain the site of PSAM wave prime, which contains points P masked by SKA and SAK prime, where P is a point corresponding to a record in the session 1 set SA, where in the second session, the attacker will finally obtain the set of PSAMA, which contains point Q masked by SK and SK prime, where Q is a point corresponding to a record in SA prime. Finally, M will learn the cardinality of the intersection between SA and SA prime, which by demasking the PSAMA prime and the PSAMA. To solve this problem, we use TLS channel bounding mechanism, and in our opinion, the root cause of such attack is that the attacker can use the mask the message in one session to another session. So to solve this problem, we banned the ECDH PSI session to the underlying TLS session by using the TLS channel bounding mechanism described by RC document of channel bounding for TLS 1.3 that we exported the key material EKM for the TLS from the underlying TLS session and use it in the hash to call procedure and take the middle attack as an example, where record SA will be masked to the point on curve with EKM, but the record in SB will be converted with another key exported key material EKM prime, since A and M and B and M are using different TLS sessions. That means even if RA and RB are the same, they will be matched as the point are different. We also use KDF for truncation. That means we also design a truncation mechanism to reduce the overhead of data transmission. And the data in the second round can be truncated as no scalar multiplication will be performed after that round. But the truncation may also raise the problem of false positive, where different records are matched incorrectly.
1 minute left.
The calculation, we also calculate the false positive rate, and we use KDRS functions to truncate the binary representation of EC points rather than directly cut the binary string. The output of KDF can be seen as uniformly distributed strings, and we also calculate the false positive rate with the birthday bound. We only provide two truncation options, which are 128 and 192. And we do not allow the implementer to use self-defined truncation option because the birthday bound is hard to calculate for non-expert. Okay, that's the end of my presentation. Thank you very much for listening. I'm Yu Chen Wang, and you can find me with my email, and this is the link of our draft. Thank you very much.
Thank you so much. Questions? Going once, going twice. Okay. Okay. Let's go to this. Thank you. Thank you so much. The MIME Franken mechanism.
Hi, I'm Rowan.
Just a moment. I'll pass slide control to Clicker. And yes, you can start.
Hi, I'm Rowan. I'm very active in the MIME working group, more in instant messaging interoperability. So MIME is a protocol for interoperability of instant messaging systems. It is a bit unique in that the flow for sending a message can go through up to 5 entities. So say Alice is a sending client, or Alice's client is a sending client. A message goes through the client, through the sending provider A, to a quote unquote hub provider, then to a receiving provider, and then finally to a receiving client. So a C to S to S to S to C protocol. So the hub in that diagram is responsible for the ordering and fanning out of all messages. It gets to see the application messages go by, but they're end-to-end encrypted. It does not get to see the content. When a message goes through, it attaches a received timestamp, which is used by the rest of the protocol. In the case of MLS handshake messages, these are proposals and commits. It gets to see the contents of those, and so it knows the list of participants in the room and their respective roles. Like if someone is a moderator or an admin. The local provider knows about its own clients. So it knows which groups its clients belong to and when one of its clients sends a message. That happens to be using whatever protocol the local that provider uses, because the client to its own server, its own provider protocol is out of scope of Mini. But it doesn't, that local provider doesn't know anything about the participants in the room from other providers. Likewise, on the receiving side, what we call the follower server, follower provider, doesn't learn anything about the sender of a message, doesn't know the members of the group, and obviously does not know the contents. Okay, so a very important requirement for people who want to have busy instant messaging systems that interoperate is to be able to report abuse. In order to report abuse, we want to be able to find out whether certain messages are authentic or not, and there's various requirements. This is my synthesis of those requirements. The receiver of a message can report a message that it receives as allegedly abusive, and it does that to the hub. That includes sending the plain text of the allegedly abusive message or messages. The hub can't read the contents of the messages under normal circumstances, but it can if they are reported. The receiver can't take a message, can't construct something and say, this is an abusive message that was sent by Alice, if Alice didn't actually send the message. Likewise, Alice can't deny that she sent a message that was indeed abusive. The hub needs to know the sender of the message in order to enforce policies, because sometimes maybe a message would only be allowed to be sent in a particular context. But we can't rely on that happening at, for example, the local provider, because the local provider doesn't even know the participants of the room and certainly doesn't know the policy in the room. Then let's see, a few efficiency things. We don't want the receiving client to have to store the ciphertext indefinitely to report a message, because that would be bad for the, that would be bad security if we're keeping along secrets for indefinitely for a message. The hub shouldn't have to store the ciphertext indefinitely either to verify that they received a particular message. Motherhood and apple pie, we don't want to rely on anything that is particularly heavy to implement, but one very, very important consequence is that we don't want to add extra round trips before sending a message, because that would be particularly painful for clients, especially on high latency connections, like certain mobile connections. Finally, if I have, let's say that I'm Bob, and I have an old device, and I want to get a new, I have an old phone, I want to get a new phone, I should be able to back up my messages, restore them on my new device, and I should still be able to report a message as abusive from the new device, even if I didn't actually receive it. Okay, so the mechanism that Mimi came up with is similar to the franking scheme that is used by Facebook and WhatsApp. The sending client creates a per message salt. It includes the salt, its identity, and the room URI inside of the message that it sends. It generates the franking tag. It's basically a hash of some stuff covering the message, and sticks it in the additional associated data in the MLS message when it sends that message. The hub, it gets that franking tag. It generates it has the sender, the room URI, and the timestamp. So that's basically who the from, the to, and the time, and uses that franking tag. It encrypts that using a key which the hub needs to keep track of for a batch of timestamps. It adds an integrity check over the things that it is about to send, and it forwards it to the receiver. Finally, the receiving client, it decrypts the message, it re-verifies the tag and the integrity check. If those are not correct, it throws the message away. Okay, so this is the crypto construction that we used with a few annotations. So M is the message that would be sent over MLS, and F of this is just there is a composition of those four things and some other stuff that gets turned into the plain text. Let's see. The encryption in C1 and C3. This is a gross simplification, but it just how MLS encrypts encrypts a private message. This is just a sort of a representation of that. There is a per message application ratchet, a per message sender ratchet that's used. So there's some different keys that are used in this process. Given the lack of time, unless somebody wants to stick on this slide, I'm going to go to the next slide. Now, for the integrity check, what the draft Felix, did you have a?
It wasn't the requirements, go on.
Okay. Yeah, so one of the assumptions here is that for the integrity check currently takes advantage of an individual draft in MLS called the associated parties draft. This allows a group that has a secret for its members, which changes as the membership of that group changes, to have a sort of parallel set of keys, which are for the members plus the hub provider. And so there is a shared secret which is available on any given epoch, and it doesn't include someone who used to be in the group or will be in the group later. But when the person is added to the group, they suddenly get that particular epoch's secret. So the integrity of this hub timestamp and the frank are provided using an HMAC. It is possible that we could provide the same level of integrity using a signature, but we would need to come up with some additional key management around how we handle key derivation and so on.
30 seconds.
Finally, when you go report a message, it is sent directly to the hub. Okay, so what we really want is people who are crypto folks to be able to review this mechanism. Felix, you had a question.
Yeah, I'm curious about the requirement around reporting that you shouldn't be able to abuse someone of a message they didn't send. There are some messages
Sorry, could you say that again slower?
Yeah, the requirement, receiver can't attribute a bogus abusive message to a sender. There are protocols like Signal, which were designed to be deniable, right? So it seems like
what real use case is that solving?
Well, I don't want to discuss whether deniability is a requirement. Like, that's not for me to decide. But there are messengers who say this is a requirement.
Deniability is not a requirement in Mimi.
Okay, so that excludes interoperability with Signal then.
Signal has excluded interoperability with the rest of the world.
Okay, thanks.
On its own, without anything to do with technical or protocol requirements. Deirdre.
Yes, Deirdre.
I've helped a little bit reviewing some of these constructions. Please take a look. There is non-trivial cryptographic design happening over here in Mimi and on this franking stuff.
That's why we're here.
Yeah, so I encourage CFRG participants to go take a look. It is both interesting and non-trivial. So far, it looks pretty good, but I would encourage more wide review. But thank you, Ron.
Thank you. And
thanks, everybody.
Please take it to the list one more time, and we'll be happy to have the last presentation, please. So, advantages of interview. Haruhisa, please take the clicker.
Hi, my name is Haruhisa Kusuge. This talk shows the importance of interview as kind of an alternative of MCAM. Let's get started. Here's a quick overview. I'd like to introduce interview first. Interview is a post-quantum key encapsulation mechanism used for secret key sharing, and it is one of around 3 candidates of NIST-PQC competition. And it's based on lattices of polynomial rings, as with MCAM, but the hardness assumption is different from MCAM. And we believe that interview must be standardized at IETF because of these 4 reasons. I'd like to explain the reasons later. And here's the question. Are you interested in the CFRG working on the standardization of interview? We'd like to discuss this topic on the mailing list after the meeting. Okay, there are 4 reasons why standardization is important. And the first reason is this. There are some advantages of MCAM. There are 4 advantages, actually. And the first one is the most important. N2 has no patent issues. It's patent-free. So if you want, you can use N2 in any kind of applications. And the second, N2 had a long history without security issues. It's been 30 years, almost 30 years has passed after the proposition. It's unlike MCAM, MCAM has only 6 years after the proposition. And third, N2 has a flexibility in parameter set, such as lattice dimensions. Such flexibility doesn't exist in MCAM, and flexibility enables kind of the optimizing performance or security or balancing them, depending on the application. Last, N2 is masking friendly. It's very easy to do the masking implementation because it doesn't use the F4 transform. But fortunately, there is a disadvantage in N2 because key generation is really slow. But with some optimization in key generation, I guess we can use N2 in any kind of situation where MCAM is applicable. The second reason for the standardization is this, mature specification. Our draft is based on the round 3 submission to NIST-PQC, and it's kind of stable. We don't need to change anymore. And we have already written down the draft and submitted to the CFRG, and we have revised once. So it's a very good point. We have a stable specification, right? And we have industry adoption of N2. And there are 2 examples. I'd like to skip them due to the limited time. And we have future plans for further adoption. There are 3 plans, actually. The first one is LibreOKS. LibreOKS is the open source library for PQC. And the N2 existed in LibreOKS in the past, but it is erased. But after some negotiation with the board of LibreOKS, the addition of N2 has been decided. Second, we will launch a project to standardize IKV2 with N2. There's another project to standardize IKV2 with MCAM, but we want to do the same thing for N2. And last, we will update N2.org. It was used for the standardizing in the NIST-PQC, but it was kind of abandoned for a long time, so we'd like to update to use it for sharing the information. these tasks is really challenging. We still have many challenging tasks ahead. So we are looking for teammates aside from other organization. And we'll have a public site meeting for N2. So if you're interested, please join this meeting. The meeting will be held tomorrow. Okay, here's the summary. So we'd like to discuss on the standardization N2 on the main set from now. Thank you very much. That's all.
Thank you. Deirdre?
Thank you. One thing, patent encumbered. MLChem has all the patents in 2 patent portfolios open to all implementers, users of implementations, deployers of protocols using implementations of MLChem, unencumbered by the agreement with NIST. So there's that. The construction of NTRU, at least in the 2019 specification that I could find, at first glance, does not have very nice binding properties. I just looked at it in the last 5 minutes. So using it in some of the places that we're looking at using either these hybrid chems or MLChem, you might need to look at it a lot closer. The lack of an FO transform might have some pluses in terms of, you have to do less work for implementation stuff that you just mentioned, but it's very powerful and it saves you from these other attacks. And the lack of an FO transform, we may have moved beyond that in terms of chem design for security deployments. Why NTRU, not NTRU Prime? NTRU Prime is the one that's deployed in SSH, OpenSSH, and is being floated about in other places. That's it.
Hi, I'm Sean Turner. I'm not a cryptographer, just a process weenie. I think that the working group or the research group needs to strongly consider, if they adopt this, the floodgate will open for all the ones that didn't get selected out of the 4th round or the final round. So I think you probably need to come up with a plan to figure out what you're going to do. Thanks.
Thank you very much.
Thank you. And we have to finish. We can move to the mailing list with this if you want. You can send a message to the mailing list. Thanks all. Sorry for being a little late. See you. Thank you so much.